sigma n equals 1 to infinity, negative 1 to the n plus 1 over 2 to the n. So number one, the condition number one is that the limit of the sequence equals 0. That is, in this case, the limit without the alternating factor. So that's just 1 over 2 to the n. And in this case, well, clearly this limit is 0. So the first condition is satisfied. Second condition, the sequence is decreasing. 1 over 2 to the n plus 1 less than or equal to 1 over 2 to the n. Is this inequality true? I mean, the exponent on the left-hand side is larger than the exponent on the right-hand side. That means it's going to give us a larger number on the left-hand side and giving us a smaller overall result. So this is true. That means we can go ahead and find the absolute value of the series. So this one will converge for now.
The little I looks like 0. It's supposed to n goes to infinity.
Which one?
The I first.
Which u?
First condition limit.
Oh yes, and infinity. Thank you. Thank you. All right. So that's the absolute value of negative 1 to the n plus 1 over 2 to the n. Well, again, what is this absolutely or absolute value bar is going to do? Well, so these absolute value bars will cancel out this alternating factor, because those alternating factors output a set of negative ones and ones. Because of the absolute value bars, all those negatives become positive, so those alternating factors simply disappear. Well, in this case, this is simply sigma n equals 1, not 0, to infinity, 1 over 2 to the n. Well, in this case, 1/2 to the n power. And what about this series? Do we really need to use any comparison like the previous examples?
No.
No, this is direct. This is a direct series. It's a really nice series. And what do we know about this series? It's geometric. And what does it do? Converge or diverge? So it's a convergent geometric series. So because the new problem that we obtain out of taking the absolute value of the series, it's a convergent series. Well, the original series, sigma n equals 1 to infinity, negative 1 to the n plus 1 over 2 to the n, converges absolutely. All right? It converges absolutely. Let's look at one more example. So for the next example, sigma k equals 1 to infinity sine k over k cubed. All right, well, that doesn't look like an alternating series anyway, all right? However, well, look at the sine k. Sine k takes values between negative 1 and 1, the max, you know? So it's important to highlight that part. That sine k varies between negative 1 and 1, because that's the range of the sine function. Those are the minimum output and the maximum output. So that's what makes it an alternating series, all right? So let's see. First condition is the limit sine k over, as k over k cubed, as k approaches infinity. Is that limit equal to 0? It is, right? However, how do we compute this limit, number one? Well, there's a couple of ways to go about this limit. Number one, in this case, just look at the behavior of the functions. We're looking at this expression or this function for large values of k. It doesn't matter how big k is, the numerator will just vary between -1 and 1, and divide any value between -1 and 1 by k cubed, which is a big number, infinity. That for sure is going to be 0. All right. Another way to compute this, but I wouldn't recommend you this because that'll be, oh no, actually the L'Hopital's rule wouldn't work here. It wouldn't apply here because this is not going to be an indeterminate form, because sine of infinity, that's basically between -1 and 1, and over infinity, this is not an indeterminate form. So another way to compute this limit is by rewriting this limit the following way. So would you agree that this is the same as saying limit 1 over k squared times sine k over k? I know it's kind of a weird factorization here, but there's a purpose to this factorization. That means, well, the limit of a product is the product of the limits. And this is a special limit you learn in Calculus 1. What is this limit equal to?
Equals to 1.
It equals to 1. So this is equals to 1. And what is this equal to?
0.
0. 0 times 1?
0.
0. All right. 0 times 1 is 0. Well, if you don't remember this special limit sine k over k, for this one you can use the L'Hopital's rule, the derivative of sine, which is cosine, the derivative of k, which is 1, and then, oh no, it's not going to work. Wait a minute. No. This special limit is not for k at infinity. Never mind. This special limit is only for k approaching 0. So in this case, yes, the overall limit it's still 0, but not for the reason I just erased. Actually, we're just taking we're taking the behavior into account to determine the limit. Okay. So second condition, limit. No, that's not a limit. That's b sub n plus 1 less than or equal b sub n. That is sine of k plus 1 over k plus 1 less than or equal sine k over k. All right. Is this inequality true? Yes, that's a cubed, right? Cubed. All right. Is this inequality true? Well, the deceiving part would be the numerator, because we have a sign of k plus 1 of a larger number than on the right hand side, but we have the reverse inequality symbol. That's the tricky part, the deceiving part. However, observe the denominator. We have a larger number in the denominator than in the denominator of the left hand side than on the right hand side. So this inequality is indeed true. All right. So this means we can go ahead, find the absolute value. Sine k over k cubed. All right. So, in this case, careful. So, for odd powers, like k to the third power in this case, number one, what are we going to have? So it's possible to obtain negative and positive values when we cube a numbers. You know, when we cube a negative number, we get a positive number. We get a negative number. But when we cube a positive number, it's always positive. So in this case, well, because we're interested in the interval between 1 and infinity, the absolute value bars are not necessary for the k cubed. However, they will be necessary for sine k. All right, because from 1 to infinity we have the sine function going between up to 1 and between -1 and 1, right, and all the values in between. Well, so in this case, we need to use the comparison test. So we need to come up with something simpler to compare it with.
1.
Compare with. So let's see if there is a simpler series that sort of looks like that original series, so we can compare it with. And again, whenever we're using the comparison test, think of something like a geometric series, well, or a P series, yes? 1 over k cubed, that is correct. Sigma k equals 1 to infinity, 1 over k cubed. All right? Yes, that's true. So, that means that when we do the direct comparison test, we need to show that tiny is less than or equal to small. All right? So in this case, well, is the absolute value of sine k over k cubed, is that less than or equal to 1 over k cubed? This is definitely true. I mean, you can omit the k cubed in the denominator. It's the same quantity. However, what is absolute value of sine of k, or what are the values of sine of k? Oh, again. What are the values of the absolute value of sine being attained in this case? Because its absolute value, it's not going to vary between -1 and 1. It's going to vary between 0 and 1, right? And any number between 0 and 1, it's definitely less than or equal to 1. All right? So this is true. This means this guy right here converges. And backtracking to the original series, this means sigma k equals 1 to infinity sine k over k cubed converges absolutely. All right? Converges absolutely. All right. What if instead of using direct comparison test, we use the limit comparison test? All right, I'm going to do both ways so you can see the difference. I mean, we're going to use the same series to compare with it. Recall that whether we use direct comparison or limit comparison, we compare with the same series. However, for the limit comparison test, we said limit a sub n, which is the original series, the original problem, this one right here, and b sub n, which is the test series, as n approaches infinity. Well, in this case, it's going to be k. All right. So this will be limit absolute value of sine k over k cubed divided by 1 over k cubed as k approaches infinity. Well, weird quotient, but again, dividing by a fraction, it's the same as dividing by the reciprocal of the fraction. So this is limit absolute value of sine k over k cubed over 1, k approaches infinity. And well, we may go ahead and divide out the k cubes. That's going to leave us with the limit of the absolute value of sine of k, all right, as k approaches infinity. Now, here is where we get tricky. How do we evaluate this limit? We need to be very careful because my advice in this case, we can use properties of limits to compute the limit inside the absolute value bars, and then whatever we get out of that limit, take the absolute value bar, all right? Because I mean, I think it's a lot easier to do, you know, just like when you have a limit, the square root of x, as x approaches 5, for example. This is the same as saying the square root of the limit of x as x approaches 5. Those are properties of limits. So we can do the same with the absolute value function. We can do absolute value of the limit of sine k as k approaches infinity. Now the question is, what happens at k equals at infinity for the sine function? in some sort it does not exist, right? But that does not exist has a special identity in this case. We need to, I mean, for this particular case, we can express that DNE in a symbolic way. So, I mean, let's go all the way to infinity. What does the sine function do? Oscillating between what values? And
0.
between not 0, I mean, just a sine function. Between -1 and 1. Okay, so absolute value of -1 to the n. Right? That's what the sine function does at infinity. Now, take the absolute value of -1 to the n. What's that? 1, right? Positive? Finite? So we meet the conditions for the limit comparison test. So you have two options to compute this limit. Choose the one that you feel more comfortable with in the end, right? Because sometimes it's a little weird to come up with or to put things together to show tiny less than small or huge greater than big. Well, you have another alternative, but just make sure to keep in mind these subtleties here. These which are the properties of limits, right? Okay, so this is the end of this section.
Wait. When you were computing whether or not whether the series converges or diverges with the previous method, why were you able to say that it was the absolute value of sine k over not the absolute value of k?
Oh, yes, good question. Because so here we're intersetting the interval from. So why did I keep the absolute value bars for sine and not k cubed? Okay, yes. So this is the real number line, -infinity to positive infinity. However, we are only interested in the interval from k equals 1 to infinity. So k cubed, raise any positive value to the third power. That's always going to be a positive, so no need for absolute value bars. However, what does the sign do, even whether for negative values or positive value? That still oscillates, right? So we need to keep the absolute value bars to honor that property, if you will. All right. And in fact, that makes easier to look at this inequality here, because when we look at this absolute value of sine k, that means it only varies between 0 and 1, and any number between 0 and 1 is for sure less than 1. All right? Good question. Thank you. All right, let's have a look at the ratio test. The last two techniques, ratio test and root test. All right, so ratio test. The ratio test is going to be your best friend for factorials. Ideal for factorials. So this is the first time we're going to look at infinite series involving factorials. This is also an alternative for alternating series. All right. Well, so let's look at the specifics for the ratio test. Number one, so we're going to create a quotient. The quotient between the original rule shifted by 1 over or divided by the original rule. We're going to take the absolute value of that, and if the limit, so there are three case scenarios. Number one, the limit is less than 1. In that case, the series converges, and in fact, this one happens to converge absolutely, and that's because we're taking the absolute value of the expression in this case. Second case scenario, the limit is a number greater than 1 or infinity or DNE. Series diverges, basically blows up to infinity. And if the ratio test outputs our limit equal to 1, the test is inconclusive and we have to look at a different test. Maybe some comparison, maybe n term for divergence, maybe the integral test, anything that we have learned before these last two tests. So let's have a look at some examples for this. All right, so sigma n equals 1 to infinity. -1 to the n squared over 3 to the n. Well, here we have an alternating series, right? Well, actually, doing the alternating series, well, for the part of taking the limit, that would have involved taking the limit of n squared over 3 to the n, and we would have had to use L'Hopital's rule, in fact, twice until we annihilate the n squared term in the numerator, so we're able to compute the limit. And that would have been overkill, right? However, with the limit, with the ratio test, set up a limit, a sub n plus 1 over a sub n, that's limit of the original rule, -1 to the n plus 1, that is everywhere I see an n, in the general rule, shift that n to n plus 1. So that's n plus 1 quantity squared over 3 to the n plus 1, and then divide by the original rule, -1 to the n squared over 3 to the n, and approaches infinity. All right, yes, a lot of terms, a lot of factors, ugly looking fraction, no worry. Number one, there's a lot of things we can do here. Number one, cross out the alternating factors. And why can we do that? Well, because we have absolute value bars surrounding the expression, right? So those absolute value bars are going to take care of it. And well, so that's going to leave us with limit n plus 1 squared over 3 to the n plus 1 divided by n squared over 3 to the n as n approaches infinity. Well, so we can simplify this weird looking quotient by dividing, well, by in this case multiplying by the reciprocal of the denominator. So that's going to be limit n plus 1 squared over 3 to the n plus 1 times the reciprocal of the denominator, which is 3 to the n over n squared. And here is the part where we're going to start doing the algebra to simplify this expression and in the end compute the limit. So n plus 1 squared, let's square the binomial. Limit n approaches infinity. That's well, actually I don't think we need to keep writing the absolute value bars, because we already use them to simplify or to get rid of those alternating factors. But it doesn't hurt to keep writing them. Yes?
Can't you simplify to get plus 1 and 3n? Like, can't that just simplify to like 1/3?
Yes.
Okay.
Yep, that's exactly the next step. So that's n squared plus 2n plus 1 divided by 3 to the n times 3. What did I do here? Well, a to the m plus n, this is equal to a to the m times a to the n, basic laws of exponents, right? And then over here, that times 3 to the n over n squared. So what's going to happen here? Number one, cancel 3 to the n with 3 to the n. And I think that's the only thing we can simplify, and that's good enough actually, because
Maybe we can drag the 1/3 out of the limit.
we can do that, or we can leave it there so we can easily see how we're going to compute the limit. Yes, in some cases I take it out. In this case I'm going to leave it inside. N squared plus 2n plus 1 over 3n squared. And well, I think it's easy to see what the limit will be. Polynomial over polynomial, both degrees match. What do we do? No need to L'Hopital's rule actually.
We just
It's 1/3. It's just a ratio of the leading coefficients, which is, and this number, well, let's see, what do we have to do? We have to check for 3 things. Number one, for the limit to be less than 1, greater than 1, or equal to 1. In this case, 1/3 is less than 1, So the series converges by ratio test. All right. So that's our first example in ratio test. Let's look at another one. For the other one, n factorial. Oh, we have factorials. So limit n plus 1 factorial over 5 to the n plus 1 divided by the original rule n factorial over 5 to the n as n approaches infinity. So, and again, dividing by a fraction is the same as multiplying by its reciprocal. So that's going to be n plus 1 factorial over 5 to the n. How about 5 to the n times 5? Let's do that in one step. And then that times 5 to the n over n factorial, which is the reciprocal of the division we had in the previous step. So from here we can actually divide out the 5 to the n's, but at the same time now we need to simplify the factorials. Remember how we spent a good minute simplifying factorials at the beginning of the chapter, because we're going to need them here. So again, in order to simplify factorials and so that our limit is not written in terms of factorials, we need to simplify by expanding between the largest of the factorials. In this case, which one is the largest factorial? N plus 1 factorial or n factorial? N plus 1. So that's going to be limit n approaches infinity. So that's going to be n plus 1. So n or n minus 1, n minus 2, n minus 3. Well, do we really need to expand to many factors? Just up to n, right? Because that matches the one in the denominator over here. And that's over 5, 1 over n factorial. Cancel out, divide out the n factorials, and we're left with n plus 1 over 5. And what's this limit equal to?
Infinity.
Infinity. All right. And well, this means the series diverges. All right. Let's do another example. Letter C. N equals 0, sigma n equals 0 to infinity of negative 1 to the n over n squared plus 1. Let's set up the limit. Or this is not equal to, actually, this is arrow limit negative 1 to the n plus 1 over quantity n plus 1 squared plus 1 divided by the original expression negative 1 to the n over n squared plus 1 as n approaches infinity. Okay, let's do one thing at a time. So let's not freak out with how ugly this looks. I agree, it looks ugly, but I mean, these alternating factors just go away because of the absolute value bars here to the rescue. And well, essentially, check this out. Essentially, this is going to leave us with an invisible 1. Do we agree with this?
Yep.
And an invisible 1. That's going to be then limit n approaches infinity 1 over the quantity n plus 1 squared plus 1 times the reciprocal of this, which is n squared plus 1 over 1. And well, how about we expand the binomial in the denominator of this first factor? All right. Limit n approaches infinity, absolute value of n squared plus 1 over, well, that's n squared plus 2n plus 1. But this plus 1, how about make it a plus 2? All right. Sounds good? That becomes a plus 2. And again, check this limit. Polynomial over polynomial. The degrees match. What's the limit here? Well, in accordance with the ratio test, what is this going to tell us? Test inconclusive. Test inconclusive, right? So we have to go and use a different test. Well, check this out. This is an alternating series. And the alternating series contain a 1 over n squared plus 1, which is clearly decreasing, and the limit is 0. So that so far converges, just converges. Now, the absolute convergence, take the absolute value of this, that's going to be 1 over n squared plus 1. That can be compared with a simpler series, which is 1 over n squared, which is a convergent P series. So going that alternative, this will converge absolutely using the alternating series test. Alright? But I mean, in this case, we're practicing on the fact that this will be inconclusive using the ratio test. When you're doing the homework, when you're on the exam or a quiz, if you get an inconclusive, most likely you will have to go about another test until you find out that either converges or diverges. Okay, letter D. This one is a weird one. All right. So this looks like this weird product right here: 2, 4, 6, 2n, 2, 5, 8, 3n minus 1. So that looks like a factorial, but it's not a factorial, because the factorial it's the product of all the numbers below n. For example, 5 factorial, that's 5 times 4 times 3 times 1, and we stop there. All right? In this case, no. We have this like increasing products. In this case, 2, 4, 6, and then we can keep writing this product by adding more terms. You know, that would have been 8, 10, and 12. So it's a sequence of all even numbers, and the ones in the denominator, well, these are the sequence of integers given by the rule 3n minus 1. It's actually an arithmetic sequence given by this general rule. All right. In the same way that we needed to simplify factorials depending on how we need to. For example, 6 factorial is the same as saying 6 times 5 times 4 factorial maybe. So we can cancel a 4 factorial with some other 4 factorial in the denominator. But another way to say 6 factorial is 6 times 5 factorial. What if we want to simplify 6 factorial over 5 factorial? Well, then we use this factorization. Or maybe 6 times 5 times 4 times 3 factorial to divide out some 3 factorial. So there's many different ways to express a factorial. But that's going to depend which one do we use? Well, the one that fits our needs. So in this case, we're going to apply this same situation with this sort of factorials that I would like to call them sequential products in this case, because we're multiplying these factors based on this given sequence, right?
So the numerator I can write it as 2 to the n power times n factorial.
2 to the n 5 times n factorial. No, well, this one doesn't involve factorials. Actually, this is a product in the reverse order, in an increasing order, not in a decreasing order like the factorial. So the reason I go about this one is because, well, another way to express a product, for example, what if I want to write down the product of the first 50 numbers? Well, I'm not going to write all the numbers from 1 to 50, all right? I'm going to use the compact notation. So that's 1 times 2 times 3 dot 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 times 49 times 50. All right, that's the product of the first 50 numbers. I don't care what that value is. We don't care. We're just expressing this infinite product. I mean, this product like this. But another way to express this product, and that depends on our needs. Maybe I need the 48 to show up. So 48, 49, 50. Maybe I need the 47 to show up as well. and these three expressions are equivalent, right? Well, we need this idea to understand how are we going to deal with this sequential product right here, all right? So, okay, let's set up the limit. So this will be limit -1 to the n plus 1, 2, 4, 6. Well, this 2n will get shifted by 2n plus 1. And that 2n becomes, when we distribute this n plus 1, isn't that going to become 2n plus 2? But be careful, check this out. I'm going to leave a space here. 2n plus 2, and I'm going to write a couple of question marks here. What is that going to be here? All right? And that's 2, 5, 8, dot, dot, dot. Okay, this 3n plus 1 minus 1. So that's 3n. And then 3 times 1, which is 3, minus 1. Isn't that at minus 2? So that's the last term when we shift. What's going to be here? Mystery for now. Mystery. Divide this madness by the original 2, 4, 6, dot, 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 2n. Which one? Yeah, 3 times. So 3 times n, that's 3n. And 3 times 1 is 3, but minus 1? That's what I meant, right? Yeah, that's what I meant, but not what I wrote. Thank you. And that's 2, 5, 8, dot, dot, dot. That's 3n minus 1. Number 1. Yes, this looks madness, but at least we can get rid of the alternating factors. Well, that's something. So, remember that sequence I wrote before? The 1 times 2 times 3 dot 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 49, 50. Well, the ratio test asks us to do the n plus 1 term. If I added one more term, that would have been the 51, right? The number 51, that will be the next term in the sequence. So, all right. In this case, approaches infinity, limit, and approaches infinity. So that's 2, 4, 6, dot, 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 space, 2n plus 2 over 2, 5, 8, dot, 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 space, 3n plus 2 times the reciprocal of this madness in the denominator, that is 2, 5, 8, 3n minus 1, 2, 4, 6, 2n. Alright? So, the idea is to cancel factors, alright? However, check this out. I can't factor 2, 4, 6, 2n plus 2 with 2, 4, 6, 2n because those do not comprise the same chunk, isn't it? The chunk in the numerator ends at 2n plus 2 while the chunk in the denominator ends in 2n. Alright? So, for this reason, so in this case, let's call this the n plus 1 term. So this 2n plus 2 came from doing the n plus 1 term, right? So I need to write the second to the last, which is the n term. But what's the n term based in the original? Isn't it 2n? And what's the second to the last from 3n plus 2? Isn't it the 3n? 3n minus 1? Alright, and only then we can divide out 2, 4, 6, 2n with 2, 4, 6, 2n. And then we can divide out 2 5/8 3n minus 1 with 2 5/8 3n minus 1, and that's going to leave us with limit n approaches infinity of 2n plus 2 over 3n plus 2. And this is 2/3. Now, is 2/3 less than 1, greater than 1, or equal to 1? Less than 1. That means converges.
Shouldn't that be less than 1 or less than 2?
Yes, less than 1. Yep, less than 1. So converges by ratio test.